We now take a look at two additional examples for calculating a center of mass. If you take a moment and look at this example and the subsequent example, what you'll see is that both of these cases involve an object that has a uniform mass density. So actually, there isn't going to be any distinction between calculating center of mass for these problems and calculating center of shape as we did in section 7.1. That's okay because these are good examples and it's good to have practice whether we're doing a center of shape or center of mass calculation. But when we get to the try me problems, we'll look at a couple where there would be a difference between center of mass and center of shape. So in this example, we have a spinner for an airplane propeller, which is given by this particular geometry. It's an object of revolution made by taking a parabolic shape and revolving it around the x-axis. And we'd like the mass of the spinner and the location of its center of mass. And because the density is uniform, that just means that we need to find the volume. And again, the center of shape won't be any different than the center of mass. One thing about this problem is that there's a couple of different ways we can look at this. We can use, I mentioned previously that for three-dimensional objects like this, we would only be looking at bodies that were objects of revolution, and there are kind of two traditional differential elements that we would use to look at a problem like this. One would be a circular disk element, and we've used that previously. We also could have a thin circular shell element. We've not used that yet in one of our examples. So I'm going to do this problem both ways, first with the circular disk element and then with the cylindrical shell element. And if we do it correctly, we'll see that we get the same result no matter how we do it. So the first thing to note here is that we're going to have to formulate an expression for the differential volume of our disk element, and that dV is going to be equal to the area of the disk, which is going to be a function of x, times its differential thickness dx. We're going to be integrating over x. And we have the bounding surface y as a function of x. That's going to give us the radius of the disk as a function of x. It's also the case that every material point within that disk is at the same x position from the yz plane. So in this case, our x tilde, the center of the disk element, is just going to be equal to x. So our volume will be the integral over the x domain of dV. We're going to go from 0 to 0.2 meters. That's where we have the tip of the propeller. We have pi r squared of x dx, and so that's going to be 0.1 minus 2.5 x squared quantity squared dx. It will be useful for us to expand this out, and this becomes 0.01 minus 0.5 x squared plus 6.25 x to the fourth. So as we're just integrating polynomials, I could write this as pi times 0.01x minus 0.5 over 3x cubed plus 6.25 over 5, which is 1.25 x to the fifth, and that's evaluated between 0 and 0.2. We get no contribution from the lower index, it's just the upper index that contributes something. And if we calculate that, we get that the volume is equal to 3.351 times 10 to the minus 3 meters cubed. The mass of the object then, because it's homogeneous, is just the volumetric mass density times the volume. So we have 2,700 kilograms per cubic meter times that volume, and that gives us a mass of 9.048 kilograms. Okay, so we know that the product of the centroid times the volume is equal to this integral of x tilde dV. X tilde is just x, so that means we can write this as pi times the integral from 0 to 0.2, 0.01x minus 0.5 x cubed plus 6.25 x to the fifth dx. That integral is 0.005 x squared minus 0.125 x to the fourth plus 6.25 over 6 x to the sixth, evaluated between 0 and 0.2 meters. And when we plug all that in, we get 2.094 times 10 to the minus fourth meters to the fourth. So our x-center is the ratio of these two integrals. We have 2.094 times 10 to the minus fourth meter cubed, meter to the fourth, over 3.351 times 10 to the minus third meters cubed, and that number turns out to be 0.0625 meters. For our second solution, we're going to use this cylindrical shell element. This is a little bit trickier than the disk element. If we think first about the disk element, we were integrating along x, and at x equals 0, the disk element had its largest radius, corresponding to y equals 0.1 meter. And then as we moved from x equals 0 out to the end of the propeller at 0.2 meters, the radius of the disk simply fell continuously until it went down to 0 and we got to the tip of the propeller. In the case of the cylindrical shell, our differential thickness is going to be in y, and so we're going to be integrating from y equals 0 up to the top of the boundary at y equals 0.1 meter. And if we think about the shape of the cylindrical shell element as we go from y equals 0 to y equals 0.1, we see that there are two parameters that are changing at once. Both the height and the radius of the cylindrical shell are going to be functions of y. So if we're near y equals 0, our cylindrical shell element is going to be this long, thin thing. The height of it is going to tend to be the total length of the propeller, 0.2 meter, and it has a very small radius. The differential element shown in the figure is kind of intermediate between the tip and the base, and then as we get towards the base, our cylindrical shell element is going to look more like a pancake. So we have both radius and height that are changing with y. What we have to do for the height is simply invert the expression that we had here describing the bounding curve. So now we're going to write x as a function of y. That's fine, and that is the height of our cylinder as a function of y. The radius is just y. Every material point at a particular value of y, every material point is at the same radial position. And so what we're going to get now for the differential element dv, we're going to have, it will be the circumference of the cylindrical shell, which is 2 pi r. R is going to be equal to y, but I'll just leave it as 2 pi r for the moment, times the height times the thickness. So that the 2 pi r times the height is the surface area of the shell, and then its thickness is just dy. This is going to be 2 pi times y here, so this is going to be 0.2 root 1 minus 10y times dy. And our x tilde is the center of the differential element, and now that's just going to be the center of that cylindrical shell, which is half the height, h over 2. So that's going to be 1/2 times 0.2 root 1 minus 10y. So the parameters here are a little bit more complicated than we had for the disk element. So now let's see what that means in terms of evaluating the integrals. So now for our volume, we're integrating now over y, so we're going from 0 to 0.1 meter. And we have our expression for dv. So we have 2 pi y times 0.2 root 1 minus 10y dy. So we could write that as 0.4 times pi, integral from 0 to 0.1 y root 1 minus 10y dy. So this integral is a little bit more difficult to evaluate than just the simple polynomials we had earlier. I'm going to let u be equal to 1 minus 10y. And then I can see that du, an increment du, would be equal to minus 10 dy, or dy is equal to minus 0.1 du. Now notice that at y equals 0, u is equal to 1, and at y equals 0.1, u is equal to 0. So first I could write this as the volume is equal to 0.4 pi times the integral from 1 to 0. I can then invert this expression and write y as a function of u. So my first term in the integral is y. I could write that as 0.1 times 1 minus u. Then I have the square root of 1 minus 10y, which is the square root of u, times dy, which is minus 0.1 du. Now our indices are reversed here. They're going from a larger value to a smaller value. We want to invert that, and we have a negative value here. So we can turn this around and write the volume as 0.4 pi integral from 0 to 1, 0.01, 1 minus u root u du. So we have 0.004 pi integral from 0 to 1, u to the 1/2 minus u to the 3/2 du. And that integral is something we can evaluate quite easily. That's going to be 2/3 u to the 3/2 minus 2/5 u to the 5/2 evaluated between 0 and 1. And so what we end up with is the volume is equal to 0.004 pi times 2/3 minus 2/5, which ends up being 4/15. And if we plug those numbers in, we once again get 3.351 times 10 to the minus 3rd meters cubed. That number had better match the value we got using the cylindrical disk element, and it does. The second integral we have to evaluate is the integral of x tilde dv, and that's going to be, again, the integral from 0 to 0.1. Now, x tilde was h over 2, so that's 0.1 root 1 minus 10y. And then our volume element, again, was 2 pi y times 0.2 root 1 minus 10y dy. That actually turns out to be a little easier to evaluate because those two square roots are going to multiply together and give us a much simpler result. So what we end up with here now is we have 0.1 times 0.2 times 2 pi that we'll bring out in front. We have a 0.04 pi integral from 0 to 0.1, and we have y times 1 minus 10y dy. Okay, now that's very easy to evaluate because, again, we're just back to polynomials. That's y squared over 2 minus 10/3 y cubed between these limits. That ends up being 0.04 pi times the first term ends up giving us 0.005, and we have a minus 10/3 times 0.001, and that again turns out to be equal to 2.094 times 10 to the minus 4th meters to the 4th. So once again, our x center is the ratio of these two integrals, and that number is equal to, again, 0.0625 meters. So it doesn't matter which differential element we use. If we're doing the problem consistently, we should get the same result no matter how we do it. Now for our last example, we're going to have the same geometry essentially, but now we're dealing with a hollow, thin titanium shell which has a small but non-specified thickness that's embedded in its areal mass density of 13 kilograms per meter squared. Again, we want the mass of the spinner and the x position of its center of mass. And so we're going to have a geometry now that looks like this. This is going to be a little bit tricky because our differential element involves this circumferential strip, but the thickness involves an arc length dl, And as I mentioned in the previous section, we have to turn that increment dl into an integral in either x or y, and that will complicate things a little bit. So let's take a look at this. So we're going to use this circumferential element as the basis of our calculation, and the area increment dA then will just be the circumference 2 pi r, which is a function of x, and again that's going to be given by this bounding surface y, times a thickness dl. And we're going to integrate this over x, so this is going to be equal to the square root of 1 plus dy dx squared dx, and that will allow us to integrate over x. So we'll note that given the bounding curve, dy dx is just equal to minus 5x, and so dl will be equal to the square root of 1 plus 25x squared dx. Our x tilde, the center of the differential element, is again just going to be x. Every material point within that strip is the same distance from the yz plane. It's just x. So now our area is going to be the integral from 0 to 0.2 meters of 2 pi times the radius, which is just the bounding surface y. It's 0.1 minus 2.5x squared. And then we're multiplying that by dl, which is the square root of 1 plus 25x squared dx. I'm going to make a substitution here. I'm going to let s equal 5x. And so then ds is equal to 5 dx. And so if I then rearrange the individual terms in this integral, you'll note that if we go from x equals 0 to 0.2, that corresponds to an integral of s from 0 to 1. And I can rearrange this a little bit and write this integral as a sum of two terms. The first one goes like 2 pi times 0.1, and then I end up with a 5 in the denominator as I'm making this change in variables from x to s, and I'm integrating from 0 to 1 root 1 plus s squared ds, and I get a second integral then, which is minus 2 pi times 2.5, and now I end up with a 5 cubed in the denominator because I've got a change in variables involving the x squared here and also the dx here. And so then I end up with an integral from 0 to 1 of s squared root 1 plus s squared ds. Unlike our previous examples, these two integrals are much more difficult to evaluate in analytical form. So let me just state right here that this is exactly the kind of thing I would not include on an exam. I do not expect you to recall all the tricks and substitutions that you can use in calculus to take an analytical form like this and evaluate the integral analytically. So I'm just going to write the result down and we'll just use it. So I will say here, occasionally I will do this, I'll just say calculus happens, and what we can show, we can either show it by using a variety of substitutions. We can also use a symbolic manipulator like Maple or Mathematica. If you're old school, you can look these things up in a table of integrals. And what I'm going to do is just write the results down, and then if you want to verify it, my suggestion is that you simply differentiate the right-hand sides to confirm that it gives back the integrands. But if I have a parameter a, so this is for a equals a constant, a real constant, it can be shown that the integral of the square root of a squared plus s squared ds is equal to this. So again, you can try differentiating this right-hand side with respect to s and verifying that you just get back the integrand. Similarly for this integral, the result looks like this. And if you're so inclined, you can differentiate this right-hand side and verify that in fact you get back the integrand. So for a equals 1, we can take a look at what these individual terms are going to produce between the limits of 0 and 1. In particular, I'll just call your attention to the natural log term. With a equals 1 and s equals 0, we're going to have a natural log 1, which is also just 0. And so, for instance, for the first term, for this integral from 0 to 1, root 1 plus s squared ds, for the upper limit on the first term, we have just square root 2 over 2, which is 1 over root 2. And then we have plus 1/2 natural log of 1 plus the square root of 2. And then at the lower limit at 0, we lose the first term because s is equal to 0, and we lose the natural log term because we end up calculating natural log 1, which is also 0. So this is the entire result for the first integral, and that number turns out to be equal to 1.1478. For the second term, we might note again that the lower index is going to give us no contribution because at s equals 0, the first two terms go away, and the natural log term at s equals 0 will again be a natural log 1. So we just actually have the three contributions from the upper index. The first one is going to be 2 to the 3/2 over 4. So that's 2 root 2 over 4. And then the second term is going to be root 2 over 8. And then we have a minus 1/8 natural log 1 plus root 2. And that number turns out to be 0.4202. So back to our area, we had 2 pi times 0.1 over 5 times now 1.1478 minus 2 pi times 2.5 over 5 cubed times 0.4202, and that number turns out to be equal to 0.09144 meters squared. And given the fact that we have this areal mass density for the titanium of 13 kilograms per square meter, that product ends up giving us 1.189 kilograms for the mass of that shell. Okay, now we also have a second integral, which is the integral of x tilde dA. And x tilde, again, is just x. So we could write this as the integral from 0 to 0.2 x times 2 pi r dl. And I can use the same substitutions I used before. And what I'm going to end up with now is that this integral could be written as 2 pi times 0.1. I get another factor of 5 in the denominator as I choose to write s equals 5x. So because I have this here now, I'm going to have a 5 squared in this denominator, and I'm going to have the integral from 0 to 1 s square root of 1 plus s squared ds, and then I have a minus 2.5, minus 2 pi times 2.5, and now over 5 to the 4th, integral from 0 to 1 s cubed root 1 plus s squared ds. Now these integrals are actually quite a bit easier to evaluate than the previous ones. I'll just note, if you want to prove this to yourself, this second one, well, the first one we can evaluate directly. That won't be any great issue. The second one we can integrate by parts if you want to do this. I won't go through it, but if you use the variable substitutions, u is equal to s squared and dv is equal to s root 1 plus s squared ds, then you can go through and use integration by parts to prove this result. But the results end up looking like this. The first term can be evaluated directly, and that is 1/3 times 1 plus s squared to the 3/2 between these limits of 0 and 1. And the second term looks like this. When we're all done, the numerical value that comes out of this is 0.007228 meters cubed. And that means our average position for this shell is the ratio of these two terms. And that number turns out to be 0.079 meters. Now, if that seemed like a very difficult problem, it was. Again, I will avoid these types of very difficult integrals on exam problems, but it is still good practice to go through the process of setting the integrals up, even if you're not evaluating them by hand. As you go on throughout your academic career, you're going to learn to use a lot of different computational tools. Even if you're using either a symbolic manipulator or some kind of computer software package to evaluate the integrals still have to make sense and you still have to know how to use them. So it is valuable to be able to at least set these up. Just not so valuable to have to remember all the tricks of calculus to get the results in analytical form.